Good afternoon. Magandang hapon po sa inyong lahat mula sa Pilipinas. Buongiorno a chi è collegato dall'Italia. Welcome to today's POLI-TECH story by the Politecnico di Milano, the Polytechnic University of Milan, that embodies the excellence of Italian and European higher education system in the fields of architecture, design, and engineering. My name is Alessandro Milani. I'm from the Philippine Italian Association. You may wonder why you have received the invitation and the form you filled up to attend this meeting. This webinar came from us. So we are a cross-cultural organization that since 1962 have been weaving ties between Italy and the Philippines by working in different fields, language, for instance, we teach Italian and Filipino language. And we're in Italian language, we are pioneers in the Philippines, and we still have the most important Italian language school in the country. And social, we recently opened a patronato, which mission is to extend assistance to citizens, students, workers in their mobility between the two countries, Italy and the Philippines. We also assist in dealing with claiming benefits, such pensions, for instance, or scholarships, etc. Cultural and educational activities, and in this we work with different countries and partners in the Philippines. We are co-founders of Unique Philippines, and we are part of the European Cultural and Education Group, which organized the European Higher Education Fair, which finally, that's a good news, is back to on-site event. It will be in this coming November 18 and 19 in Mandaluyong at Shangri-La at Mall. I mentioned this because aside from the fact that some of you might be interested to join, but also because it's thanks to the European Higher Education Fair that we started to cooperate with Italian universities and the Politecnico di Milano in primis. And this is the reason why we developed with the Politecnico some projects. We started to work together on some project, and we are now here for the POLI-TECH Stories series of webinars. Today's topic will be on wind engineering, and it will be focused on the role played by the wind tunnel in defining the wind effect on large infrastructures via tests and scaled models. Speaker of today is Professor Daniele Rocchi, Professor of Wind Engineering at the Department of Mechanical Engineering at the Politecnico di Milano. Professor Rocchi's research activity mainly covers wind impacts on infrastructure, aeroelasticity of suspension and cables stayed bridges, detachment of vortexes from squat bodies, investigation of the dynamic responses produced by the fluid structure interaction of sidewalks, stadium covers, building, wind generators, and rail vehicles. Professor Rocchi is also a member of the committee for aerodynamics effects provoked by rail vehicles. And in this field, his research primarily focuses on studying the effects caused by lateral wind, ballast lifting, slipstream, overpressure pressures in tunnels. Today, the presentation will be divided in 3 thematic sets of 10 minutes each, more or less. And it will be followed by 5 minutes for question and answers. So please write your emails in the chat box. We will collate them, and we will address them at the end of each thematic part. We will have a special guest to moderate the Q&A. Her name is Professor Lori Lisa Bulayog. She's the Dean of the College of Architecture and Engineering at the University of Science and Technology of Southern Philippines. She has a doctoral degree in mechanical engineering, and she's also a researcher in electronic system design at the University of Surrey in England. So without further ado, I leave the floor to Professor Daniele Rocchi. Buongiorno, Professore.
Good morning to everybody, and thank you for the invitation. Hello, everybody. As Alessandro said, I prepared this presentation divided in 3 topics. So we start talking about long span bridges, and then we move to tall buildings, and then to high-speed trains. So let's start with the previous one. So the wind effect on bridges. First of all, a quick recall of what are wind effects. So I think in our common life, everybody experiences the effect of the wind and the effect of the forces exerted by the wind on structures and also on our body. In order to study this kind of effect, we needed to just identify what are the parameters that rules these aerodynamic forces. First of them is the relative wind speed. If we run against the wind, we perceive a lot of effort, while if we run in the same direction of the wind, we perceive less effort. So what does it mean? It means that what is important in the definition of the aerodynamic forces is the relative velocity, so the difference between the main speed and the wind speed. This is not only something that for sure we know, but what is interesting is that the relationship between the aerodynamic forces and the relative speed is not a linear dependency. So we have the dependence on the square of the relative speed. It means that if we double the wind speed, we make the aerodynamic forces 5 times larger. And another aspect that is important to understand is that the larger are the exposed surface to the wind, the larger is the aerodynamic forces. So if we have to fix this concept, we must say that forces are linearly dependent on the surface exposed to the wind. Then there is another aspect to take into account, and this aspect is due to the shape of the body that is exposed to the wind. This is a test we performed in our wind tunnel on a skier, and the idea is to identify the amount of the aerodynamic load that is reported in the plot with the blue line with the aerodynamic position of the skier. So you see then when we have a reduction of the force, it depends on the aerodynamic position taken from the athlete. So in this case, it's the best aerodynamic position he can take because the aerodynamic forces is the lowest as possible. And this is inserted in our formula through an aerodynamic coefficient Cx. So if we take the full equation, we can say that if we look to this experiment, we have a ping pong ball that is excited by the aerodynamic force coming from a air dryer. And we can see that the ball is in a sort of equilibrium. This equilibrium is the equilibrium between the weight of the ball and the aerodynamic forces. What is important for our understanding is that the aerodynamic forces can be split in 2 components. One is the components aligned with the wind direction, and the other one is the component perpendicular to the wind direction. The previous one is called the drag force, and the second one is the lift force. So if we move to our subject, our topic, a bridge that is exposed to the wind is exposed to this kind of forces. So the larger is the bridge, the larger are the forces. And if we look to the structure, we can say that the larger surface is those of the towers, the main cables, and the deck. But among these three main parts of the structure, the most important one is the deck. And the deck is in the same condition of the ping pong ball. So it has its own weight that is supported by the cables of the bridge, and it is exposed to the aerodynamic forces divided in a lift force and in a drag force. If we consider that the bridge is very, very long, we can say that each section of the deck will be exposed to a different wind, but on each part of the deck, the wind will produce a pressure distribution around the deck itself that is responsible for the lift, the drag, and also an overturning moment effect. And these three effects can be explained or can be described through the equation we already saw in the previous slides. This is not only the way to describe the aerodynamic forces, because aerodynamic forces also depend on the motion of the bridge. In this animation, you see a bridge that is rotating, and on the right side, a reproduction of what is the flow field around the deck. We can see that anytime we rotate the deck, we perturb the fluid field, and as a consequence, a different aerodynamic load will be applied to the deck itself. So the motion of the bridge is able to change the aerodynamic force. And if this change of the aerodynamic forces is applied in a direction that is able to introduce energy in the system will increase the amplitude of the oscillation. And this is what occurred to the Tacoma Bridge. In the late 1914, this bridge was built on a river, and there was, after the completion of the construction stage of the bridge, there was a windy day that was able to excite the structure with this torsional motion. And the explanation of this torsional motion is due to the interaction between the motion of the bridge and the aerodynamic forces. This was a disaster, since at the very end of the story, the bridge collapsed. So, and after this failure in the scientific world, it was started a deep investigation of what was the causes that produced this catastrophic failure. The explanation to this failure was, as I said, due to the interaction between the aerodynamic forces and the motion of the deck, and this is due to the bad aerodynamic shape selected to build this bridge. So this bridge, showing a very large frontal area, generate aerodynamic forces that acts in favor of the motion, and so that produce instability. So the solution for that is to perform an aerodynamic optimization of the shape of the deck, and this can be done in several ways. One way is using deck sectional model, so a reproduction in the wind tunnel of a small part of the deck, and this small part of the deck must behave exactly as the full bridge. So if we look to this video, we can see that this deck model is suspended on springs, and also you can recognize some lumped mass at the end of the model, in order to reproduce not only the vertical but also the torsional motion of the deck. And when we switch on the wind in the wind tunnel, we can measure what is the response of the deck in order to investigate if this motion produces instability or not, and in case of instability, to modify the shape of the deck to remove this kind of instability. The result, another results that can drive the optimization of the shape of the deck is the measurement of the aerodynamic forces on the deck sectional model. So many times these deck sectional models are equipped with force balances. In this case, the force balance is inside the model. And the model can be, for example, rotated in order to change the exposure to the wind. And on the plot below, you see the coefficient, the aerodynamic coefficient, that is the variation of the aerodynamic forces changing the angle of attack of the deck itself. And this can be done rotating the model, but we can also investigate the aerodynamic forces moving the deck sectional model along different axes, so horizontally, vertically, or torsionally. And to this purpose, we developed this system that is a system with some electric actuators that are able to move the deck sectional model in different directions. So a video of the system with the sectional model is this one. So we can reproduce any kind of motion that the deck can have under the wind, investigating if the aerodynamic forces that arise due to this motion are stable or are unstable. And this is the setup in our wind tunnel. All this kind of wind tunnel tests, so the test on suspended deck sectional model or on sectional model moved by this kind of systems, produce the optimized solution. And after the Tacoma Bridge collapse, one of the most popular solution was a single box, like these three examples taken by three different suspension bridges. In this case, this kind of shape do not have 1 degree of freedom instability that was the kind of instability of the Tacoma Bridge. But this is not the end of the story, because it was discovered that there is another kind of instability called Fluttering Instability that affects also this kind of single box deck solution. And this kind of fluttering instability is a specific coupling between the vertical and the torsional motion of the deck that under some critical wind condition, so at a certain wind speed, produce this kind of instability. So in this animation, you see that the motion is no more simply torsional like in the Tacoma Bridge example, but here we have a vertical and a torsional motion that are coupled by the aerodynamic field force field, and they behave in a way that when the deck is moving upwards, we have that also the aerodynamic force is pointing upwards. And when the deck is moving downwards, also the aerodynamic force is pointing downwards. So it means that aerodynamic forces are always aligned with the motion of the deck. And so they are very effective in producing large vibration of the bridge up to reach some a sort of instability that produce the failure of the structure. So the aim of the wind tunnel test is that we already optimized the shape of the deck. So the aim of the wind tunnel test is that we can't avoid to have this kind of fluttering instability, but we want that the critical wind speed that produce this kind of instability is so high that is not probable. So in other terms, this critical flutter speed must have a return period that is very, very long. So you see here in this plot that if we increase the wind speed, the return period, that means how long I have to wait in order to see this kind of wind, becomes very, very long. So if I build a structure, I have to select the specific return period, and I want to find a solution in the wind tunnel, granting that the critical flutter speed is above the return period, the velocity with that return period. And this improve the research in the bridge, in the wind engineering field, on and other solution was developed. In this case, you can see that we are in recent years, we passes for the very long span bridges. So for those bridges having more problems with aerodynamic loads, we passes from a single box to a double box. So the deck is composed by 2 separated boxes, or even 3 different boxes. And the reason for that is if we pass from a single box to a multi-box solution, we reduce the aerodynamic coefficients, and as a consequence, we increase the wind, the critical wind speed to very high conditions. This is, for example, the solution adopted for the longest span bridge in the world, that is the Cali bridge in Turkey. This bridge has a main span longer than 2 kilometers. And if we look to the solution of the deck, we can recognize 2 different boxes connected with cross beams. So we have 2 different crosses carry-on road vehicles that are connected with some lateral beams. This is a solution that we already tested. We also tested in our wind tunnel. And this solution is taken by previous studies performed at the Politecnico di Milano on the Messina Bridge. The Messina Bridge is a bridge that was studied to connect the Sicily to the mainland. Sicily is an island in the south of Italy. And in that case, the main span of the bridge was 3.3 kilometers. And another requirement was the bridge has also to carry on the railway traffic. So not only road traffic, but also railway traffic. And for that bridge, a 3-box solution was developed. In the wind tunnel, we don't test only deck sectional model, and we don't only optimize the deck sectional model, but we also have the possibility to study the full bridge condition. So in order to do that, we usually build what we call an aeroelastic model of the full bridge. An aeroelastic model is a model that has the same shape as the real structure, but has also the same dynamic behavior of the real structure. The reason for this kind of test is to investigate the behavior not only of the deck, that even if is the most important aerodynamic part of the bridge, is not representative of the full bridge, but the behavior of the whole structure. And in this video, you can see that this kind of bridge, this kind of aeroelastic model is able to highlight what will be the real behavior of the structure when the structure will be exposed to the wind. In this video, the wind is highlighted with smoke. That is a typical techniques to show what is the flow in the wind tunnel, and you see the motion of the deck. Of course, if the aeroelastic model is properly designed, it is also able to reproduce what we call the flutter instability. So if we see to this video, we see an increase in the amplitude of the motion that becomes no more controlled up to the failure of the structure. So we can really investigate what is the limit of the stability, of the aerodynamic stability of the structure itself, and to demonstrate that this wind speed is far above the wind speed with the return period selected to design this kind of structure. Another possibility opened by this elastic model is also to test some very critical conditions for the bridge that are the construction stages. So when the bridge is not already completed, the structure has less stiffness, less capability to withstand aerodynamic loads. And in this picture, you see three different stages of the construction of a bridge, starting from the early stages when only a small part of the deck is positioned, up to the very end when the deck is more or less completed. And another possibility is also to test the behavior of the towers in freestanding configuration. You see that in this case, this kind of towers suffer from vortex-induced vibration. What does it mean? That the flow produces some vortexes around this structure that are able to excite the structure in this way, producing large vibration. This is not only a problem of the tower, but can be also a problem of the deck. This is a bridge that was built very recently in China. This video was recorded in 2020, in May 2020. You can see the motion of the deck. This motion of the deck is due to a bad aerodynamic optimization of the deck itself. And you can see a motion that is vertical, purely a flexural mode. And it is excited by the vortex shedding from the deck. Okay, I think I don't know if we are on time, but I think it's a good point to see if we have some question from the audience.
Sorry. Right, thank you so much, Professor Rocchi. Yes, it was indeed a very nice presentation for our, especially for our students in civil engineering and mechanical engineering. We have a question here coming from a civil engineering student. So the question goes like, in the Philippines, being in a tropical condition, which is somehow always visited by a typhoon, and our wind here, our weather condition is a bit tricky. There's a question of, should an engineer be able to review and retrofit all structures, including glass windows, that are susceptible to wind-related damages?
Okay, thank you for the question. This kind of very specific wind effect like typhoon are very well studied because there is a very long scientific activity on that. And there are also some wind tunnels that are dedicated to reproduce wind having the same characteristic of hurricanes, typhoons, and so on. And also the standard in the region where this kind of wind effects are frequent ask for specific studies and specific design computation in order to assess that also in that very particular strong wind condition, the design of the structure can withstand the aerodynamic loads that occurs. What we saw here are what in the scientific field are called synoptic wind, a wind that are very constant in mean wind speed with some turbulence inside. And the situation is very different from, for example, a tornado, where you have that the tornado itself is moving and have a very fast and very quick variation of the aerodynamic forces. So there is a specific field in wind engineering dedicated to that.
Okay, thank you so much, Professor. Okay, yes, indeed. There are, because in the Philippines, we are visited at least 26 typhoon a year. So which always our structures are somehow affected by this wind condition. So
Yeah.
thank you. Thank you so much.
Okay, do you have other question on bridges? Otherwise, we start talking about buildings.
We have another question, Prof.
Okay.
Next question is, could applying a hydraulic piston on a parallel to the wind direction reduce vibration?
Hydraulic piston in doing wind tunnel experiments?
I think so, yes.
Okay. Okay, so two kind of answers. One answer is when we study the problem in the wind tunnel, we can do more or less everything. So we can attach to the deck whatever we want. We can also try to investigate some active control procedure to reduce the vibration of the deck. What is difficult is to translate it in real life, because what is very simple in a wind tunnel has the technological limits in the real life. So if you want to attach some actuators or dynamic actuators to the deck in the wind tunnel, I can put it in the middle of the bridge. In real life, I cannot do that because in the middle of the bridge, I have the water below. So usually what I can do in real life is to connect the deck to the towers, for example. But under the tower, the deck moves with very small amplitude. So the effect of the actuators is reduced by the low amplitude of the deck. I don't know if this answered the question.
Yes, thank you, Professor. Yes, indeed it does, because I supposedly my next question, you have already answered the next question, if we could apply it in real life. Thank you so much for expressing it. It's very difficult to apply it in a real application or real life situation.
No, there are other systems, maybe passive or semi-active, that will be shown later on when we talk about tall buildings, that are tune mass damper. This system will not have the request to be attached to the ground, but can be fixed only on the structure. So this kind of devices can be used easily.
Hey, I think we have one more question. Last question, Proof.
Yep.
We have here, which types of bridges would be the most ideal for the aforementioned location with frequent typhoons?
So which
types of bridges that would be ideal for places that are frequently visited by typhoons?
Bridges?
Bridges.
Bridges. Okay.
Bridges that is appropriate.
Okay, thank you. But the answer is similar to what you do in European climate condition, because what is dangerous is for the bridge is the instability, aerodynamic instability that can occur, and this instability can be reduced if you have very optimized shapes of the deck. At the moment, the most optimized shapes are the multi-box solution. So even if the wind is stable, or even if the multi-box, if the wind is not stable like in a typhoon, if you reduce the aerodynamic forces, you reduce the effect. Since typhoons are very strong, and they can produce a very peculiar situation where the wind, for example, is no more aligned to the deck, but has a very large angle of attack. we can, for example, for sure select a multi-box solution, but we have to study it also at a large angle of attack. In that case, we have to understand if the solution is strong or robust also at very large angle of attack. What is interesting is that in order to find the failure of the structure, we have to wait a lot of time. You saw in the video of Tacoma that the oscillation was continue a lot in time before reaching an amplitude that destroyed the bridge. Typhoons are very, very strong, but are also very quick. So this condition can be changed in a small time. So this could be helpful in order not to reach the unstable condition.
Okay, thank you so much, Professor Rocchi. Is there any other questions? I learned a lot from your answers, sir. Yes, indeed. I am not a civil engineer, but it's very interesting to hear all those explanations you have. So I guess here our students who are our future civil engineers in the Philippines would learn a lot from the discussion and the answers that you have provided them.
Okay.
Thank you. Okay, so I think we can proceed to our next topics, and there's no question for this particular topic. Thank you.
Okay, but at the very end, we have another question and answer time, so we can move back on bridges if a new question will arise. Okay, so let's move on the second topic that is wind effect on tall buildings. There are several effects that can occur on tall buildings. One of that is the detachment of some part of the facade and, for example, the roof, that are the region where we have the larger aerodynamic loads. In order to study this, we needed to investigate what is the pressure distribution around the envelope of the building. And the models that are used to do that are rigid model, where you see on top an example. A rigid model is different from the elastic model we saw on bridges because it is not intended to reproduce the dynamic behavior of the structure, but he wants to reproduce only the shape of the building. And this is the reason for that is the dynamic response of a tall building is smaller than the dynamic response of a suspension bridge. So the motion is smaller, and only very tall buildings can have an important effect due to the motion on the aerodynamic forces. Most of the buildings have a small dynamic response, and so it is enough to reproduce the shape of the building in order to measure the pressure distribution around the structure. There is a new thing that we have to take into account, that on the contrary of a bridge that develops horizontally, a tall building is developing in the vertical direction. And the wind has some variation in the vertical direction because the wind interacts with the ground of the earth. And on the earth, we have a lot of roughness produced by trees, by buildings, by all the obstacles that is on the surface of the earth. And so there is a reduction of the wind speed very close to the ground. This reduction is less effective if we move far away from the ground. So what we saw, what we usually say in the wind engineering is that we have an atmospheric boundary layer. So the wind has a profile like the one reported on the left, where the maximum wind speed is far away from the ground, and close to the ground we have a reduction. So this consideration has to be taken into account when we want to test a rigid model of a tall building in the wind tunnel. Just to give you an idea, the idea is to put a model inside a flow in the wind tunnel. The wind tunnel is a duct where we can produce wind using some fans to move air. And there is a model that reproduces the shape of the object we want to test, instrumented to measure pressures or aerodynamic forces. In the wind tunnel, we have in Politecnico di Milano, we have two different ducts, so two different test sections in the same wind tunnel. We have some fans that moves air. This air is initially driven at the second floor, where we have the atmospheric boundary layer test section. Is a test section where we can also reproduce a wind that is similar to what we have in the atmospheric boundary layer in real life. And in order to do that, we need a lot of space to produce the correct characteristics of the wind before the wind will exert aerodynamic loads on the model. After the test on the model, the flow is bended again to the first floor, when we have another test section where we can test object that does not require the presence of an atmospheric boundary layer. Just to give you an idea, this is an overview of the dimension of the atmospheric boundary layer test section. We need 36 meters in order to develop the wind with the proper characteristics. The maximum wind speed in this section is 15 meters per second, and we have a turning table that is used to change the exposure of the building to the wind, because the wind is fixed, so we cannot change the direction of the wind. We change the exposure of the object. So this is our test section. Our test section is 14 meters wide and 4 meters high, in order to host the rigid models of the buildings. The other test section is a different one, is a test section where the maximum wind speed can be 50 meters per second. It's smaller because we need to increase the wind speed, so we need to reduce the section of the testing section. That is 4 meters wide and 4 meters high. And in this section, we can, for example, test the tech sectional model of the bridges. This very large facility is needed because if you think that, for example, this tall building is 200 meters high, and we need to scale down the model to host the model in a 4 meter height of the wind tunnel. And for example, for this application, we choose a scale factor of 1 to 100. To host a full bridge of 2.6 kilometers in 4 meter horizontal dimension of the atmospheric boundary layer test section, we need to use a 1 to 200 geometrical scale. How can we obtain a wind that is similar to the full scale one? As we can see from this comparison, if we are in different position on Earth, so if we are on the sea, or if we are in a urban environment, the profile is different, and the atmospheric boundary layer has different characteristics. But these characteristics are connected to the obstacles that on the Earth produce this effect. So the idea is to behave exactly as nature does. So putting some obstacles in the flow and putting some roughness on the floor, we are able to obtain in the position where we put the model we want to investigate a flow that has similar characteristics to the real one. And of course, if the model, in this case, the model is a mall, and this mall is positioned in a urban area where we have already some buildings already built, we need also to reproduce the proximity models, so all the buildings that are in the surrounding of our building, in order to have the same effect we have at full scale. So coming back to our problems to measure the pressure distribution around the building, in this example, you see a building or two buildings in their environmental urban area. Each of these buildings is equipped with some pressure taps. Pressure taps are holes that are drilled on the surface of the building model and connected with some tubes to an instrument that is able to measure the pressure on the surface. So for example, for this building, we have 256 positions where we can measure the pressure. And the results is that we can plot the results for each position where we have this pressure tap, and to investigate if we have some problems in some part of the building facade. In this case, the most dangerous condition are the part where we are in blue, in dark blue, because dark blue means negative pressure. Negative pressure is suctions that can detach the glasses from the facade or the roof of the building. We test this rigid model changing the exposure, so changing the direction of the wind, and we can select what are the worst conditions where we measure the most negative pressure in some part of the facade, and this value is the value that is used to dimension the fastening system of the facade. This is not only the only problem of tall buildings, but tall buildings have also the problem of vortex shedding. Vortex shedding is something that occurs when the wind is interacting with the shape of the building. If we look to this animation, we can see that this obstacle that has a circular shape is able to produce vortices in the wake. These vortices in the wake, while they are detaching from the building, produce also some aerodynamic forces on the building itself. And if we change the shape of the building, we change the fluid dynamic mechanism of this vortex shedding phenomenon. We have also to take into account that this phenomenon is able to produce a motion of the tall building, because this force that is produced by the vortex shedding is a periodic force with a specific frequency that, if it is equal to one of the natural frequencies of the tall building, can produce a resonance effect on the building itself. So in order to study this problem, you can study using, for example, an elastic model similar to the model described for the bridges. In this case, it can be seen how an elastic model of the supporting frame of the Dubai Eye is able to highlight possible problems of vortex shedding on this kind of structure. What is the solution to avoid that we have a vortex shedding from a tall building and this vibration induced by the vortex shedding? We can have different solutions. Most of the solutions are aerodynamic solutions, and there is also some structural solution. Among the aerodynamic solution, one solution is to change the shape along the height of the building. So if the shape is irregular, it's less likely to occur the vortex shedding. So if we pass from a square with sharp edges with a square with some rounded or cutted edges, we can have a reduction of the vortex shedding phenomenon, and especially if we change this shape with the height of the building, because the global effect on the whole building is less coherent if we move from the ground to the top of the building. Another solution is to change continuously the shape of the building. So we have some building that exploit this solution to reduce the vibration of the building. Of course, the vibration of the building can have a comfort, can lead to a comfort problem for the people that are inside, that are working inside the building itself. These solutions are tested in the wind tunnel. For example, this solution is the solution taken from the tallest building in the world that is built in Dubai. And you can see that this model is a model that is tapered, so it will reduce the area of the floor at moving far away from the ground, and change also the shape. Other possible solution that you can find in some already realized building is, for example, to use the same shape, but to twist the shape moving far away from the ground. So the building at each floor has a similar shape, but this shape is rotated around the vertical axis. This is for an example. We have another example also here in Milano. The building on the left has a similar shape, but with this twisted architecture. A new solution is to foresee some holes in some part of the building in order to change the aerodynamic behavior at the different floors. This is an example with a very large hole on top of the building. I think the most interesting and recent solution is this one. This is a very, very slender and tall building recently built in New York. And the solution adopted to be able to build such a very slender and very regular in the shape building is to leave some floors completely empty, so to provide some voids where the wind can blow inside, in order to have a global behavior that is not coherent along the total height of the building, but have some variation in some floors, and this reduces the effect. Apart from this aerodynamic solution, there are some structural solutions that are tuned mass dampers. What are tuned mass dampers? Are dampers, so are systems designed to increase the damping of the structure, that are big masses that are connected to the structure and that are able to move. And the motion of this large mass connected to some specific dampers is able to remove some energy from the system to damp the motion of the building, and so to obtain some comfort criteria for the buildings. I think the most famous tuned mass damper is the one adopted on the Taipei 101 building that was the tallest building in the world from 2004 and 2009. This building, this TMD, is a ball, a big ball. It's a pendulum. So the mass is organized like a sphere, and the connection with the building is with the dampers you can see to the bottom. This TMD is visible from the restaurant that is on top of this building, and you can see in windy day that the tall buildings is more or less still, and you see this big ball that is moving because it is destroying some part of the energy introduced by the wind in the building. Just for mentioning other problems related to the wind and tall buildings, one is the pedestrian comfort. When you insert tall buildings in a urban environment, you are modifying the situation in that area, in that part of the city. And you can, for example, produce some speed up effect that are not comfortable for the people who is living in that part of the area. And depending of the activity that the people is doing, if it is sitting on a restaurant or it's standing or is jogging or is doing other activities, there are different thresholds of comfort. So one study that is usually done using also wind tunnel test is to measure what is the flow at the pedestrian level to understand if the presence of the new building produces some uncomfortable situation. And another thing is aerodynamic noise. So this is an example of a building built in Manchester. Once built, this building produces some aerodynamic noise that is annoying the people living surrounding this building. This is another aerodynamic problem, so it can be studied, for example, in the wind tunnel, and it is basically produced by some elements in the facade that are producing noise, aerodynamic noise. Okay, before moving to the last topic, I think it's a good time to see if there are some questions on this one.
Yes, Professor Rocchi, we have some questions. We have 2 questions here for this topic. So the first one is, what is the percentage of error acceptable in wind tunnel test to have results as close as reality? I think you are muted, Bru.
Okay, can you hear me now?
Yes.
Okay. So if you have to judge the goodness or the quality of wind tunnel results, I have to look at several things. So one is a good reproduction of the model. So we saw that we have a lot of aerodynamic solution where only some details are changed. Let's think about rounded corner instead of sharp corner. But of course, when you reduce in the scale a model, what is sharp at full scale can be rounded at small scale. So you need quality in the construction of the model and expertise. That means even if technologically I cannot have a completely sharp edge, I can put something there to produce the same effect of the sharp edge. So this is expertise of wind tunnel people. The other thing is to have a good quality of the flow. So in order to have a good quality of the flow, you need to have facilities where you have enough space to produce what is the atmospheric boundary layer effect. And of course, each facility has different quality in the flow, and this also affects the quality of the results. And the last thing is the quality of the instrumentation. Nowadays, technology improved a lot the quality of the instrumentation. We were talking about 200, but nowadays we are using 500 points measuring the pressure distribution around the building. This is possible because we did a lot of development in the instrumentation, in the quality of the instrumentation. So there are a lot of factors that contributes to the quality of the results, and you need to be an expert of the field to be able to perceive what if you are good results or not. This is the reason why people working in a wind tunnel are expertise in the field, and people designing structures must have a wind engineering formation, so background, in order to be able to understand.
Okay, thank you so much, Pearl. So I guess the percent error is really still affected by how the quality of the test itself and how we can model it in the experimental setup as the same as much as possible with what is in reality, considering all the conditions that were mentioned by Professor Rocchi. Thank you so much. We have another question. I think this is proof. They have a question. Have you done simulation on any vertical structure against wind speed of 330 km/h?
I forgot to say that the wind speed in the wind tunnel, if you have an elastic model, has some scaling rules to represent reality. So when you saw the elastic model moving in the wind tunnel, the frequencies of the motion are not the same frequencies of the full scale structure. But there are some rules, some physical rules that allow to compare the results in the wind tunnel with the full scale situation. Also, the wind speed is not the same at full scale because you are small dimension, so you need to slow down also the wind. But there are some rules to report what you measure in the wind tunnel with small wind to high speed winds at full scale. So depending on the elastic model and the site where you want to build the bridge, the building, and so on, you need to use these scaling rules. 330 km/h means 100 meters per second, more or less. Our wind tunnel can move to 50 meters per second. But 50 meters per second in the wind tunnel represent more than 50 meters per second at full scale. So we can test also to 330 km/h under specific conditions, so under specific scaling rules that we can use.
Okay, so proof, is it safe to say that you have able to done simulation in the wind tunnel with 50 meters per second for vertical structure? You have tried it, you have simulated it, am I right?
Vertical structure means buildings.
Yes.
We can do it in the high-speed section where we can reach 50 meters per second. In the largest one, where the maximum wind speed is 15 meters per second, we have a different maximum wind speed at full scale. But it depends on the dimension. If we reduce a lot the model dimension, on that model, 15 meters per second are a lot. If the model is larger, 15 meters per second are less. what is the drawback? That we want to take the model as large as possible because details, geometrical details are important. It are much more easy to reproduce details on a big model than on a small model. But then is what you are asking, another aspect to take into account. So we have also to reduce the model in a way that the maximum wind speed we have in the wind tunnel represent the worst scenario at full scale. So if we look to this consideration, we need to reduce more the building. So it's a matter of a threshold to make a geometrical good details and to have a correspondence to the maximum wind speed. But then there is also some numerical simulations you can do. So you can use some results taken from the wind tunnel for some simulation in order to represent something that occurs at higher wind speed. For example, for the bridges, you can use the aerodynamic coefficient to do some simulation. And in the simulation, you can simulate also large wind speeds.
Okay, thank you so much, Professor. So I think this was well understood by everyone. I think we have one last question for this. How long does it usually take to undergo wind tunnel test during building design?
Oh, how long in time?
Yes,
so
this
is a very nice question, because if you look to a full bridge elastic model, in order to build that model, it takes 2-3 months, because you have to redesign the structure, you have to build it, you have to test that the dynamic behavior is what you expect or not. So the design stage and the construction takes, let's say, 2 months, and the test in the wind tunnel 1 week. Because once the model is done and it is properly designed, then the wind tunnel tests are very quick. So it's much more the work, the time spent in designing the experiment, that the time taken from the experiment.
Okay, yes, I think I agree with that. Same with other system design. Thank you so much, Professor. I think, would you accommodate one more question?
Yeah, sure.
Yes, we have here a question. As per structure that are already built, meaning the structures that are already now standing, what are your solution? What could you recommend for a solution to be considered, not for the design to be retrofit in order for the building to be more resilient to high wind speed?
It's difficult to act on already built structures, but nowadays you have a double facade. Double facade are facades that are not directly attached to the main building, but are separated from the main building. So you can have an internal core, and the real shape of the building is provided by a second skin attached to the body. With this solution, especially nowadays, is really attractive from the architectural point of view, because apart from the shape, you can also play with some porosity. So you can put not glasses, but grid. So you can use elements that are porous with respect to the wind. And this porous facade had a very large effect on the aerodynamic behavior of the building itself. So some good solution also solving the problem of the vortex shedding are obtained attaching a second skin with some porous media that helps in reducing the aerodynamic loads of the building itself. So you can play with this kind of solutions.
Okay, thank you. Perfect. So hopefully we have our students who are on their 4th year who are doing capstone project. That will be a very nice capstone topic here in the Philippines, because most of our structure proof are already, we call it, somehow the Philippines are more on retrofitting it because it's not really designed that it can stand the wind, no, that we have here in the Philippines. So thank you so much, Professor Rocchi, for giving us those insights you have that will really help our students, especially now that they are doing their capstone or their thesis. So I think we can move on to our next topic, Professor.
Okay. I will move on the high-speed trains. I will try to be a little bit quicker because we are running out of time. The most important effect in the interaction between wind and vehicles is the crosswind. This is something that is very well known, for example, in the aircraft field. You know that if you have strong winds, you have some problems in landing. And it's also very well known also on road vehicles or railway vehicles. And the most risky effect on railway vehicle is the overturning of the vehicle produced by lateral wind. We have some accident concerning the crosswind effect on vehicle. This is recent, 2015. We are in United States. In this case, the problem was on freight vehicles, so trains carrying goods, and with a very large lateral surface, because in this in the picture on the right, you can see that they use double stack containers, so you have a very, very high trains. But we have these problems also here in Europe. For example, in this video in Switzerland, you see in a windy day in winter, you see the overturning of a vehicle produced by lateral wind. These effects, I think there will be more frequent in the future, because we have also some climatic changes that can produce very strong wind more frequently than in the past. This is, for example, a storm in the UK in 2022. And here you see the overturning of a lorry on a track on the road. So in order to study this problem, we need to understand what is happening. In this case, we have to understand that the presence of a lateral wind modified the aerodynamic behavior of the train. So we have to sum up the running speed of the train with the wind speed of the crosswind. So we have a composition of two velocity. One velocity is the train velocity, and the other velocity is the wind velocity, that are not aligned, but are more or less perpendicular. And so the final wind, so the relative wind that we saw at the beginning, is the responsible for the aerodynamic forces, act on the vehicle with a skewed angle. So we have two effects. One effect is that the angle of attack, so the direction of the wind, beta W in this figure, is changing. And according to this angle of attack, also the aerodynamic coefficient CF will change. And another effect is that we have a reduced velocity that play with the square in this formula, that is increased by the sum of the train velocity and crosswind velocity. This study started with the development of the high-speed trains, because high-speed trains are moving at 300 km/h. And if you look to this number for high-speed train, the train speed is much higher than the peak wind speed. So most of the relative wind speed is produced by the train motion itself. Then, if we look to the angle of attack or to the exposure of the train to the relative wind speed, for high-speed train, we are talking about to 0 to 30 degrees. While if we reduce the train speed, we increase this angle beta, and we are talking about 0 to 60 degree. These are two considerations that will be useful later on when we will compare the situation of high-speed train with conventional trains that are not moving at 300 km per hour, but they are moving at, for example, 200 km per hour. But as I told you, most of the studies started when in Europe we start developing the high-speed train lines. The previous one was opened in Italy, and then it will be developed all around Europe. The final aim of this study is to understand if there is a risk of overturning and to study what are mitigations of the risk. So the basic idea is, okay, if we find out that the risk is too high, we need to decide what are the mitigation solution we want to apply. For the railways system, we have two possible solutions. One solution is to put some wind barriers on the side of the railway line, so in order to reduce the wind that is acting on the passing vehicle. The other possibility is to reduce the speed of the train when the train enters some areas where the risk of overturning due to crosswind is too high. Since the trains are connected to a system that can control the train speed, if you are able to measure what are the windy conditions in the region and you decide that the windy conditions are too risky, you can, for example, reduce the speed of the train in order to reduce the aerodynamic forces. In order to apply this, one of these two possible mitigation solutions, we need one basic information. What is the maximum wind speed that the train at a specific train speed can withstand without overturning? So the idea is to study the problem and to find this kind of plot where on the horizontal axis we can put the train speed, on the vertical axis we can put the crosswind velocity, and the points represent the threshold of overturning. So the situation where the train starts overturning. If I have this information, I can, for example, perform a meteo analysis of the railway line, find out what are the most risky, the most windy part of the line, and decide if we want to protect the line with some wind barriers or if we want to reduce the train speed in that area. To obtain this kind of information, there is a methodology that was developed in recent years that start from some aerodynamic coefficients measured in the wind tunnel. So in this case, the contribution of the wind tunnel is in defining what are the aerodynamic coefficients used in the methodology to compute the aerodynamic loads, and to perform a dynamic simulation of the train, introducing in the dynamics also the effect of these aerodynamic loads. Looking at the results of this numerical simulation, we can find out what are the combination of crosswind speed and vehicle speed that produce critical conditions. One consideration is that the effect of the aerodynamic loads that want to overturn the vehicle are counterbalanced by the weight of the vehicle itself. So the weight force acts as a restoring effect that counterbalance the overturning effect produced by the aerodynamic loads. Traditional trains has a composition where most of the weight was at the end car, where locomotives were positioned. So usually the most weighty cars of the train are the end cars because they are locomotives. Nowadays, new trains have a different architecture. So all the cars in the composition of the train are used to carry passengers. And also the first and the end car are passengers cars. And the power, the traction power, is distributed in different cars along the train. Why I'm discussing about that is because usually the two cars of the train that are most sensible to crosswind effect are the end car. The intermediate cars have aerodynamic coefficient that are better than the aerodynamic coefficient of the end cars. If we remove weight from the end cars because there are no more locomotives, but they become passenger vehicles, and we distribute the weight along the train, it means that the new trains are much more vulnerable to crosswind effect than the previous one. And this is the reason why for this kind of train, this procedure is contained in a standard. For the homologation of the train, the train manufacturer has to demonstrate that the train passes some requirements for the crosswind stability. These are an example of experiment taken in the wind tunnel to obtain the aerodynamic coefficient. Also, in this case, we are using rigid models. So we reproduce in a reduced scale the same shape of the train. And in the example reported in this slide, the force balance is positioned inside the model. The model is positioned on a turning table in order to be able to change the exposure to the wind, and for each of the different exposure, the aerodynamic forces and the aerodynamic coefficient are measured. So if we look to the plot on the upper right side of this slide, this is the lateral aerodynamic coefficient. So is the lateral force that will produce the overturning of the vehicle. We start with an angle beta 0, where this lateral force is null because there is no crosswind. If we have an angle different from 0 up to 50 degrees, we have an increase in the aerodynamic coefficient of the lateral force. This means that this lateral effect will become more and more important. This is explained by the color maps on the left side. So if we move from 0 degree up to 30 degree, we see that on the lateral surface of the train, there is a dark red area that is increasing, and this is the pressure that is exerted by the wind on the lateral surface of the train that can produce overturning. Of course, the shape and the geometry of the train is important in the definition of this aerodynamic coefficient. And so if you look at high-speed trains, the shape is very, very smooth, and the shape is optimized also for crosswind effect. But if we compare high-speed train with conventional train, we can discover that the situation is not so different, because it's true that for high-speed train, we have a relative wind speed that is larger because trains are faster. But for the conventional trains, we have a bad aerodynamic coefficient. Bad in two ways. Since the shape of the train is not so optimized by an aerodynamic point of view, the coefficients are larger, but the train is slower, and so the crosswind occurs at a larger angle of attack, larger value of beta. And we saw before that the coefficient for larger value of beta is larger again. So it's true that a conventional train has a smaller reduced velocity, but this effect is compensated by the increase in the aerodynamic coefficient. So if we look to this plot, in this plot we have the limit condition for a high-speed train, the green line, and for a conventional train. And if we can see that the overturning is very, very similar. So a wind speed of 25 meters per second is critical for a high-speed train running at 300 kilometers per hour, as well as for a conventional train running at 200 kilometers per hour. So the same crosswind speed is critical for both these trains. And so this methodology and these studies are nowadays extended also to other trains, and also in the design of conventional trains nowadays, crosswind effects are considered. What we discussed up to now are crosswind considered as a steady state condition. So the train is running in its direction and it's always exposed to the wind. There is another risky condition that is when we pass from a situation where the train is protected by the crosswind, for example, when the train is running inside the tunnel, and the condition where the train is fully exposed to the crosswind effect. So when the train is exiting the tunnel. So for this kind of analysis, we can also perform a dynamic test in the wind tunnel. So different from what we saw before, where the train model is still. In that case, is the transient situation that is dangerous. And so to perform this kind of test in a wind tunnel, you have also to try to find a way to move the model in the crosswind condition. And this slider is one possible solution. Okay, this is the end for my presentation. I think we have some other minutes for question on all the topics.
Thank you so much, Professor Rocchi, for that very interesting, again, discussion or presentation about how it is very important to determine the wind direction and how this affect the structure. There's a question, well, I'll go through. The question is, can we automate the wind tunnel, the test of the wind tunnel?
Can you operate in the Politecnico di Milano wind tunnel?
No, can we automate?
Automate, okay.
Yes.
Okay, the process of automation is already done. So when you see the model in one position, then if you start the test, you will have an automatic system that can turn the vehicle, so can change the direction of the wind. And for each position, switch on and switch off the wind in order to record the forces. As we told before, the most time-consuming operation is the construction of the model. And in this way, modern 3D printers can allow to save a lot of time. So for example, if we talk about a tall building that has to be equipped with pressure taps, so all the tubing inside connecting the surface of the model with the instrument, with 3D printers, you can print a model with all the tubes already connected, for example. Nowadays, what you usually do, you build the model is completed, you start drilling the holes, and then you glued all the tubes and you connected the tubes to the instrument. If 3D printers will become faster and cheaper, in the future, what you will do, you directly draw the model with the tubing inside, and you print everything, also the tubes, and then make it very, very fast and quick. The problem nowadays is the cost. So especially for wind tunnel that are very large as the Politecnico one, the model are very large and the cost at the moment are very large compared to the cost of the traditional model maker techniques.
All right. Yes, indeed, it is. Now we have here in the Philippines a very small wind tunnel, and I have my PhD in IIT. Cost a lot. Okay, Professor, there are students who are interested now. So their question is, are there available position in research, such as research associate, research assistants, for potential students, PhD and master students in wind engineering at your university?
Okay. We have, of course, a different level of open position. The first one is the possibility to have the master thesis studying in the wind tunnel some problems. So usually there is a connection between two professors sharing the same interest in the topic, and the student can spend some times of the master thesis at the Politecnico performing wind tunnel test. The most popular one is PhD, because PhD is a 3 years period or more. And we have both fellowships paid by Politecnico di Milano on this kind of topics. And we have also the possibility to sign double degree agreements at the PhD level. That means the students is let me say shared by the two university. So let's say in a 4-year period, the students spend 2 years in one university and 2 years in the other university. In the 2 years when the student is at the Politecnico Milano, can use the facility. So can use all the equipment to build the model, to test the model, to analyze the results. And then there is a third level, that is the mobility between permanent staff, so associate professor, full professors, and so on. This is also possible. We hosted a professor from Canada for 2 years. We have a shorter visiting professor for shorter periods. So we have also mobility at that stage. I leave here my email. So if you need more information about the different levels, I can forward the request to the proper people inside Polytechnic.
All right, thank you so much, Professor. Yes, I think they are very interested. And if you will allow a sandwich program like other universities in US, because here in the Philippines, we have fundings from our Department of Science and Technology under the ERDP. Our PhD students will do their course here, and they will do their research in other universities, such as maybe in your university.
Mhm.
So, but then the expenses will be paid by the scholarship under the Philippine scholarship. They're just going to do their dissertation in your university. So that
Okay.
means they will have a advisor here in the Philippines, and they will have advisor in the university where they're going to do their research. So I
Yeah.
hope that will be also open and the same in your university.
Yeah. It's something that is for me very useful, because you have a lot of network connection all around the world, and sometimes you discover that some people are already working because they meet at the conferences and so on, and it's just a matter to share also human resources to do something together.
Okay, I think we have still one last question
Yeah.
here, Professor. It
Yes.
says here that thus the train length impact have also an impact on the wind force analysis aside from just the height.
Okay, the train length is it's not so important, the train length, but it's important the first car length. Since we said that the end cars are the most vulnerable to crosswind effect, of course, the longest is the first car, the most aerodynamic effect can collect. And so the length of the train is really important, not of the train, but of the first car or to the end car. This is important. And of course, the height. So we have, for example, double deck trains. So trains where the people can stand at 2 levels. Of course, this is a little bit higher. And for the overturning, this effect is important.
Okay, so there goes your answer. I think we made this question, Mr. Samuel Costa. Okay, Professor, I think there are no questions, and we are very thankful for this opportunity that you have given to us. You share your expertise to our students, both our undergraduate students for civil engineering and mechanical engineering, as well as our graduate program students, not only here in USTP, but actually with other universities here in the Philippines. So we hope that we can have another discussion like this, or maybe in another topic, that it will really be very helpful to our students. Thank you so much, Professor.
Thank you to you. It was a pleasure. Thank you.
Grazie, Professor Rocchi.